We are live.
We're live?
Yep.
Okay, great. Well, hello. If anyone is watching, thanks for joining us. Again, sorry for the slight delay in starting, but we will get smoother at this, I promise. Yeah, okay. So welcome to what is really, I guess, our first live stream of this particular format, which is going to be a kind of collaborative research working session. So on the call we have Carlos Zapata-Carratalá, and we're going to be trying to make the first kind of inroads into this project that Stephen has been talking about wanting to do, or wanting someone to do, for a very long time, which he's called the Infracalculus project. I'm not particularly sold on the name. I don't think Carlos is particularly sold on the name either. So one of the things we may end up discussing in this call is perhaps what might be a more fitting name for this particular project. But to give you a kind of brief summary of what I think the objective is. So for context, during the course of the Wolfram Physics project so far, a major theme of what we've been trying to do is to recapitulate kind of things that we know about modern physics using kind of rewriting theory and hypergraphs and so on as kind of as the raw computational substrate. But an awful lot of what we, how we traditionally formulate the laws of mathematical physics involve, spatial structure. They involve continuous geometry. They involve things like, Lorentzian manifolds for representing space-time, Riemannian manifolds for representing space-like hypersurfaces, projective Hilbert spaces for representing spaces of quantum states, Fock spaces for, as the basis for quantum field theory. All of these are kind of continuous topological or geometrical structures. And so if the Wolfram model is going to be a reasonable model for fundamental physics, it has to somehow be able to reconstruct the spatial structure of these objects from kind of discrete underlying hypergraph dynamics, rewriting system, formulations. So Infracalculus, I guess, is intended to be the project that tries to construct a general, robust, rigorous mathematical theory of how that works, right? So far in a lot of what we've done, we have some hypergraph rewriting rule, and we make some slightly hand-wavy statement about, and now we take a continuum limit and it becomes like a Riemannian manifold. And there are various notions in which we can take those limits, and various open questions about, the situations in which those limits are well defined. So, one very basic point, just to illustrate kind of what I think are some of the key mathematical and conceptual difficulties. Okay, if you take a hypergraph and you try and and you try and construct sort of something approximating a Riemannian manifold, it's very easy to do that, right? You can easily, by processes like Poisson sprinkling, you can construct hypergraphs where the induced discrete metric on the hypergraph becomes an arbitrarily good approximation to the Riemannian metric on some manifold. But then if you say, okay, this hypergraph becomes a Riemannian manifold in some limit, that's actually a surprisingly subtle statement, because you're in fact taking not one limit, but at least two and possibly three. Taking a limit as the number of as the size of the hypergraph goes to infinity, as the number of nodes or the number of hyperedges goes to infinity, but also the limit as the length of each elementary hyperedge goes to zero. And for instance, it's not at all obvious a priori that those two limits commute. And yet a lot of the mathematical apparatus that we build in the Wolfram Physics project relies on the assumption that those two limits commute. Similarly, in fact, as it turns out, when one's dealing, for instance, with graphs and hypergraphs that are produced by sprinkling processes, there's actually a third, more subtle limit that's kind of secretly hiding there, which is the limit of a kind of statistical ensemble of these things. Because in reality, typically when we say, okay, we produce a hypergraph that approximates some manifold by sprinkling points in that manifold and then connecting them with hyperedges if their metric distance is less than some value. Well, okay, that gives us a kind of discrete form of the manifold, but the continuum form of the manifold is only reconstructible as we take a statistical limit, essentially as we consider a statistical ensemble of all such sprinklings. And so, in fact, there's also a third limit that we are often taking, which is the limit of an arbitrarily large number of sprinklings, an arbitrarily large number of hypergraphs that we then sort of average over. So many different kinds of limits, many of their analytical properties still essentially unknown. And so I think the argument is, if I can give a pitch for this project, it's clear that there is a general mathematical theory that is crying out for development. And I suppose if we were to characterize it in abstract terms, it would be something like, we want to construct a generalization of this standard tower that goes from set theory to topology to analysis to geometry and so on. We want to kind of rebuild that tower, reformulate it in a way that is fundamentally agnostic as to whether the underlying structures are discrete or continuous. That all the standard constructions that we would do in topology, in differential geometry, in analysis, in functional analysis, all work irrespective of whether the underlying structure that we're operating on is a continuous Riemannian manifold or a kind of discrete lumpy hypergraph. So that would be my initial sort of pitch. Carlos, do you have comments or refinements or
No, I think as an overall program that of what Infracalculus was, I guess, intended to be what Stephen, because I remember being in one of the live streams where Stephen was defending the term Infracalculus, and I think it's I'm not against the term itself, but I think it's a bit misrepresentative of what the program that you outlined is going after, right? And I think by the way, I apologize for my voice. I told Jonathan I've had this infection for some time now, and I think I'm okay, but I'm going to apologize in advance for some raspiness of my voice. But anyway, so I think the program makes a lot of sense, and it goes nicely together with this. I mean, the fact that the physics project is based on generative hypergraphs and these models that are going to replace, in some sense, notions of axiomatic presentation and saying here's the category of all possible physical universes, and now it's just a matter of like finding your way into it, and so which one is your actual reality and so on, and more like these are the possible sort of genetics of your universe, and now you're going to let evolution play out and see where it takes you, right? I mean, I think it goes well in this context because in a way what Jonathan is pointing to is the possible existence of a theory that will be agnostic of that kind of difference in a way, right? It will be agnostic of saying that something is very axiomatic and sort of declaration based, where you are declaring all your objects from the get-go, from or something that is mostly based on generation and sort of automata-like processes and more emergent, if you like, sort of theories. And it seems that in conversations, Jonathan and I, and in past live streams, people who are following the Institute would have heard that there are patterns that seem very persistent across different fields, and of course, pure mathematicians in the audience or people who are familiar with category theory and things like that. This has been noted. It's not a realization of ours that there are these patterns that really you don't mind too much if your set is finite or it's infinite or it's continuous or it's a smooth or topological space or whatever. These patterns are usually captured in all this sort of categorical structure and sort of higher forms of mathematics more recently. But I think that what we need is something that is more, I think, catered towards application in the sense of in scientific application, not necessarily sort of technological application or something like that, but something that is catered towards computation in a more pragmatic sense, meaning you want something that is operational, you want something that gives you computing power, gives you the ability to model very directly, in the same way that you want to model the faucet in your flat, and you do some short differential equation to figure out when you have to refill your boiler or whatever, right? Something like that gives you calculus gives you a very direct way to model certain things, and it's very clear that it's adapted to that. I think what we're missing is something similar, where you are not assuming all the sort of real analysis in the background or the sort of topological structure in the background and so on, because it might be technically different, but perhaps we have a theory that can be sufficiently overarching that you don't need to specify those. And of course, the motivation being, as Jonathan mentioned, that we have strong indications that there are models that are completely discrete, hypergraph-like, this sort of very sort of almost combinatorial in nature, and we have these other models that are completely, smooth, infinitely differentiable vector fields, tensor bundles, and whatnot. And in some sense, when you squint your eyes, you can almost not tell which one is which, right? So I think that's I mean, I don't really have anything to modify from your statement. I think it's more like, yeah, this is certainly something that we should be working towards, And as for people in the audience who maybe don't know as much about my personal background, I used to be a differential geometer in a past life, in a way, before I came into the orbit of Wolfram and computation and all these kinds of things. I was a sort of full-time differential geometer. So my background is really in mathematical physics and differential geometry. And in the last, 3 years, I've been dealing mostly with hypergraphs and this more kind of discrete type mathematics. And I have to say that it's been only lately that I realized that, I was joking to Jonathan saying, am I overanalyzing my own speech when I realize that when I explain to non-mathematicians what I'm doing, I start to sound very similar now when I'm speaking about rewrite systems, hypergraphs, confluence properties of this and that. Or when, a few years ago I was talking about dynamics on a Poisson manifold and Lie algebroids and blah, blah, blah. And I suddenly realized my language is sounding very similar when explaining these two very different concepts in principle. And I was wondering if I was just being prey of, me growing older, or just being lazy, or I don't know, having some kind of, echo chamber with myself, or if there was actually some pattern. And I think after some conversation with Jonathan and, pondering about it, I think there is indeed some interesting patterns. In fact, if everything goes well, we will be having a project at the Institute where we will explore those analogies in a very acute detail, and hopefully we will have concrete results in a few months to show you, look, this is a preprint, or this is a sort of a report on the specifics of this analogy. The only thing I want to mention to add, and with that I conclude my initial statement, is that in my intuition, the thing that seems obvious that should be the translation tool between something like smooth differential geometry and hypergraph rewriting systems, or hypergraph models and discrete combinatorial structures and so on. To me, the clear translation tool is algebra in a way. It's algebraic compositionality sort of structures in some sense. And this is, again, as I said, people have noted this, and the entire industry of category, or almost the entire industry of category theory, is mostly concerned with these kinds of questions. But I think one of the lessons that I learned when I was a mathematical physicist, or a training mathematical physicist, was that if you wanted to only know the essence of a mathematical structure in a physical theory, most of the time what you had to do is to just look at it from a purely compositional point of view. So if you could understand that it was a module with a left representation on this, and an associative non-commutative algebra on there, and then there's an action of this and that. I mean, when you had that whole picture and you exhausted all the canonical information that your objects allowed, that usually characterized them almost fully, or at least sufficiently for your interests in that context in physics. So I suspect, or at least my initial intuition is going to be that algebra is going to be at least a guiding tool to draw parallels between the two fields. And of course, the ideal would be to develop something that is not just a correspondence between the two, but actually some sort of framework where we have a new way of addressing all these concepts, right? But I imagine that algebra is going to be a good tool to sort of pinpoint and to sort of locate the features of the landscape that we want to chart.
Absolutely. And so Carlos mentioned it offhandedly, but it's so. Let me stress. So as Carlos says, if everything goes well, we are in the process, hopefully, of onboarding someone to come and work full time for us for a little while, to work on exactly the project that Carlos is outlining, which I kind of consider to be. It's one of the reasons I wanted to have this stream and to really kind of get started on throwing ideas together, because that project, I think, will be, if it works, the first sort of killer app of the Infracalculus program, right? So the idea there is to say, well, we have these multi-way systems, these multi-way states graphs and evolution graphs, and these, this is hardly a proof, but they are somehow highly evocative of the discrete analog of phase spaces, right? That somehow it seems intuitively very obvious that unless there's some really foundational abstraction, some continual limit of something like a multi-way states graph should give you a symplectic manifold, with a Poisson structure, etc., in some appropriate limit. And right now, I don't think we have the mathematical technology to be able to make and prove statements of that form. If the Infracalculus program really works, that's one of the things. That's the kind of thing that I think we should be able to do. And so, it's one of the reasons why it's great to have have Carlos around, as he says, someone who used to be, and to a great extent still is, a kind of card-carrying, dynamical systems, geometric, sort of differential geometric, mathematical physics type person. And so yeah, I think one of the objectives for this stream will be to start laying, hopefully, the conceptual and maybe even some of the technical groundwork for that particular project. Hoping that goes ahead over the next couple of weeks. So maybe we should start. I can start making some notes. I apologize. Those of you who've watched streams before may notice that, to their horror, that I'm in higher definition than usual. I just changed my setup, so sorry if things go a little bit wrong. But okay, so infracalculus. I'm going to put that in inverted commas, so
yeah,
we make it clear that we're not completely set on the title. I don't know, initial brainstorming. Okay, so what is it that we particularly want to achieve in this stream? So the first thing is, I think, okay, a good place to start would just be to say, okay, so opening question to Carlos, I guess, right? So my instinct, but I'm worried that I'm being, because, okay, there's always a danger when you try and do these kind of like, let's reinvent a field kind of projects, that you end up, that the order in which you try and pursue the ideas ends up essentially recapitulating the educational system. You end up recapitulating the order in which the ideas are taught, rather than the actual true conceptual order of things, right? Like, in some sense, you might argue that, so typically people are exposed in a traditional undergraduate curriculum or something, people will be exposed to calculus long before they're exposed to topology. But arguably, that's kind of not really right. I mean, you can't really formulate the core ideas of analysis without having some notion of open sets and continuity and all these essentially topological ideas. So I want to make sure that when we do this, we don't end up making that same mistake. But so what I was going to say was, my instinct is the right place to start is topology, right? Is to essentially start by saying, let's start with a countable set, and let's figure out, what is the appropriate, if any, generalization of concepts like open sets, open balls, neighborhood structure, etc., that we could then use to kind of build off to do geometry and things beyond that. But I mean, do you think that's a reasonable starting point, or should we start somewhere else?
I think it's a reasonable starting point conceptually. I mean, we should definitely entertain this idea and discuss it briefly, at least briefly, but I'm wondering, because topology in principle is quite agnostic on the fact that sets are discrete or continuous or anything like that. So I wonder if we want to be as, because in a way, I mean, this might be contentious to say, but in a way, I feel topology is too lean for a calculus or for geometry, and certainly for dynamical systems, I would say. And I would say that metric induced topologies are much more, I would say, much more proper to the whatever it is that we're trying to get at with calculus or geometry or dynamical systems and so on. Because topology, it's just set theoretic. So from the get-go, at the definition level, you already don't have any preference towards continuum, right? I mean, it's only when you get into this sort of second countable statements or Hausdorff properties and things like that you start sort of refining to things that appear like spaces. Or certainly when you assume there's a model space and then you require continuity maps from that model space to some other spaces, and you start to define manifolds and things like that. But I guess metric, I mean, I'm not sure about this, but I would say the notion of metric and sort of proximity in a quantitative sense, and I think is probably more direct to go to because it's less obvious how you do that in a sort of intrinsic way in a discrete set, but because topology, my point is basically, you can always think of a topology on a discrete set, and you can just try to define your open sets as subsets, and I think you can lose yourself in the sort of the details of, okay, can we actually make it work as a topology? But maybe it's going to be very far conceptually from implementing notions of proximity or closeness or direction, which I think is one of the most important ideas. I mean, so is that? I mean, I'm just saying, topology seems to me a bit too lean or too neutral in a way. It's a bit non-committal for geometry, and I would say, if I were to list my desiderata for what a right generalization of geometry would be, I would say that you have a notion of proximity, which I would say does encapsulate or is encapsulated in topology sometimes, and then open sets and so on, and then a notion of direction in this sense, which perhaps together make the notion of path and path or walk or whatever. So to me, those are the more important ones to recover. I would say topology is one parsimonious way to do proximity, in a sense, to talk about essentially open sets and what whether 2 points share an open or share an open cover or and things like that. It gets there. I mean, proximity, but topology has no sense of direction whatsoever. There's no sense of, and on top of that, there's no sense of path or walks or distance and things like that, right? So I think topology would only get us sort of like halfway there, in a charitable interpretation, in my opinion. What do you think?
Right. Okay. So I broadly agree with everything you've said, and I think you've hit upon a very important point that is worth stressing. So, which is that if the structures with the core structures we're dealing with are things like graphs and hypergraphs, a very important point that Carlos has made, that is sort of implicitly making, is that something like a graph or a hypergraph is a priori a metric space. In fact, it's a metric measure space, right? It already has much more structure than a standard topological space. Now, of course, as you say, once you've got a metric, you can consider open balls that induces an open set structure. Any metric space has a natural topology, but it's not like we're starting from some raw structure that's like a topological space. I mean, that's one interesting question that I've thought a bit about, but I don't have any ideas really about, and we could maybe discuss it, is, if we agree that a graph or a hypergraph is the obvious kind of discrete analog of a metric measure space, what is what would be something more like a topological space? What, in other words, how could you take a graph and remove enough structure that what you were left with was purely the open set structure? My hypothesis, which I stated to Carlos in a private call a few days ago, is that it might be something like the transitive closure. That when you take a graph and you take its transitive closure and you're just saying effectively, which parts of this graph are connected to which other parts, and you lose all the information about the lengths of the shortest paths. That feels something more like a topological space, but I'm not sure if that's the appropriate generalization. And then effectively, the fact that there are many possible metrics that you can equip a given topological space with corresponds to the statement that there are many that a single transitive closure or a single sort of graph with several completely connected components can be the transitive closure of many possible graphs. But I don't know if that's the right way to think about it. Maybe we should, I don't know. Carlos, you can I'm going to make some pictures.
Please, go ahead.
But if you have
pictures are wonderful to aid in thinking. I mean,
right. Okay. So what I'm going to do is I'm going to try and make a graph that approximates a hyperboloid. So I do that.
Ooh. Yeah, there's a Dugan Hammock is suggesting here in the chat, one could look at the topology generated by the set of hyperedges in a hypergraph. That's certainly, once you get into hypergraphs, that's certainly a possibility that we can explore.
Although the idea of using the hyperedges as the points rather than the vertices as the points is a little bit,
I'm not sure if they are suggesting that it should be.
Or is Dugan saying that the hyperedges themselves should be the open sets?
That's the way I read it originally, but I don't know. Maybe they can clarify if they.
That's a very restricted class of hypergraphs, right? Like that obey the axioms of a topology, in that way.
Hyperedges are subsets of points. It's unclear. I think Because they said generated by a set of hyperedges.
Right. So okay. Anyway, so to illustrate the thing I was saying just earlier, right? So here's an example of all we're doing is we're taking a continuum hyperboloid, we scatter points on it by a Poisson point process, so that the probability of a point existing in a given region of that hyperboloid is proportional to the Riemannian volume measure. And then anytime a pair of points lie within a certain distance of that Riemannian metric, in this case it's 1.2, then we connect them with an edge, and so we generate a graph that. In some appropriate limit, and we'll discuss in just a moment what we mean by that limit, becomes essentially an arbitrarily good approximation to a hyperboloid. So as I mentioned before, there are multiple limits that we can take. One of them is just the limit of the number of points. So if we made this more sparse, we could have like 100 points or something, and we get a more coarse approximation.
Mm-hmm.
We can go back up to 200. It's going to do the formatting notebook content again, isn't it? Okay. But another thing we can do is we can also change the discretization scale, right? We can change the minimum length below which we treat two vertices as being adjacent. And another kind of limit that we can take is the limit as that number gets arbitrarily large. So if we make that a bit lower, we get something a bit more sparse. When we make it even lower, we get something much more sparse. So that's another notion of limit. And then, another limit we can do is we can, each time I run this function, we are getting a different graph. We're getting, so in effect, we are just selecting one element from this ensemble of all possible graphs that are produced by sprinkling into this hyperboloid. And so one way that you can, and this is the approach that, for instance, is used in causal set theory, one thing you can do is you can say, well, we can define that hyperboloid to be the ensemble of all graphs that we sprinkle into it, and for a given discretization scale. So as you make that ensemble infinitely large, that's yet another notion of limit that we can take. And again, one of the objectives with the Infracalculus. So I'll just say different notions of limit of a graph to a manifold, and I'll put this in as an illustrative example. But that's one of the kinds of questions that we would like, hopefully, the Infracalculus program to be able to answer is, what is the relationship between these different notions of limits and so on. But okay, so if I take this graph, let's call this graph. Okay, so important point, all hypergraphs are metric spaces. So what do we mean by that? Well, we take this graph and we get its list of vertices. Okay, so I can say random choice. So we'll get some random vertex. Let's say 0.1 equals some random vertex, and we'll get 0.2 is some different random vertex. And then we can say find shortest path within that graph from 0.1 to 0.2. And then I can say highlight graph. Highlight the subgraph that's induced by that. And let's style this a bit. Wait. Sorry. No? There we go. All right, okay, so here's so we've just selected two random points, we get the shortest path between them, and so this corresponds to, so this pair of points has a graph distance of 3 because you have to traverse a minimum of 3 edges to get from one to the other. And so it's not very difficult to convince yourself, if you look at this for a little bit, that this notion of distance satisfies the axioms of a metric space. So all graphs, therefore, are kind of trivially metric spaces. They are also trivially measure spaces. So we say, important 0.2, all hypergraphs are measure spaces. And so the reason for that is because we can do this construction that Stephen is particularly fond of, where we can take a point. Let's take one of those two random points that we selected. Let's take 0.1 or something. And I could say neighborhood graph. Always tripped up by American spelling. A neighborhood graph 0.1, and let's grow out a neighborhood graph of distance. No, maybe that's too dense. Let's go distance 2, and let's say highlight graph style that directive. Okay, so let's do. So here what we're doing is we're starting at, it's a horrible color. Let's go back to the red. So we're starting at some random vertex, and then we're just growing out. We're looking at all vertices that are within distance 1, all vertices within distance 2. We go further, we can get all vertices within distance 3, and so on. And so if we then take this neighborhood graph, so if I say, all vertices within distance 3, and I say vertex count of that. So now this gives me, my graph is equipped trivially with a counting measure. So what I'm doing is I'm selecting a point and I'm saying effectively, let's look at a ball of radius 3 around that point. What is the volume of that ball? Well, it's 114 because there are 114 vertices contained within that subgraph. So the counting measure or the combinatorial measure also trivially equips our graphs with a measure, as would be the case with any metric, with any corresponding metric space. So why am I saying this? I'm saying this to kind of to underline Carlos's point a little bit, to say actually the starting point that we're at is we already have a lot more structure than we do in a standard topological space. We already have a metric, we already have a measure, and so in some sense graphs are already much more geometrical than or hypergraphs are already much more geometrical than anything we could do with a bare metal topological space. So yeah, so there's an argument that maybe we just maybe we don't need topology. Maybe we just start directly from metrical geometry. I don't really know. Is there any danger from? I don't know. Yeah, is there any danger of not traversing the intermediate ground of really defining a topological space in the setting, or should we just leap directly into metrical geometry?
Yeah, it's interesting because in a way. I wonder what we would miss if we were to do that, because I mean, you can certainly, you have a metric space, therefore you can define balls, and balls give you your topology, and I really wonder how, because outside of homological arguments and sort of outside of some broader how to put it, some broad topological features of manifolds, I don't really see topology being anything but just the sort of underlying foundation that the manifold theory is built on, right? I certainly, when I'm doing when I'm doing manifolds in an algebraic way, so I'm looking at Lie algebras and Gerstenhaber algebras and algebroids and all those kinds of things, topology is basically missing. It's there allowing for those definitions to make sense, and it's providing the sort of mathematical scaffolding that gets you those precise objects in the end. But in a way, it's concealed, right? So if you were, let me put it this way, if you were to find a Lie algebra or something like a commutative algebra or a ring of which you can define the derivations, and you can get a sense of what is an internal derivation of that or what is an external derivation, and you can start to think of an analogs of, say, vector fields or directional derivatives or things like that. If you were to have those things, and in a discrete context or graphic, hypergraphic context, whatever it is, I would say that you've bypassed topology, and you probably didn't need to go there. You probably can go there, and my suspicion is that you can probably see what the topology is, but I would maybe this is my bias because I've mostly worked as a geometer and not as a differential. So I'm mostly a differential geometer and not a differential topologist, right? But in a way, even I think my differential topologist colleagues will tell you, topology is there mostly as a kind of almost like basic hardware to run the software, right? Like the software is actually your manifolds and your spaces and so on, and like it just runs on topology. It happens to be axiomatized that way, but you're rarely using arguments of finite covers or things like that, when other than showing existence for constructions, right? So it's usually a geometer will take great lengths to check that something has a global atlas, right? And so you can have a cover of charts that are overlapping, and you have all these transition functions and all those things. But arguably, that only is relevant for geometry, even in a finitary sense. So you don't have to worry about global atlases to still have many completely meaningful geometry, right? And you can certainly do geometry in a patch where there's no way of transitioning to anything, because there's literally one chart, right? You can have geometry on that chart, and by studying what the directional derivative means, or what functions mean, or what paths mean, and all those kinds of notions, right? So I am, perhaps just because of my training and my bias, but if I were to see what the differential dynamics or a sort of Poisson geometry object is like in this discrete context, I would have probably bypassed topology to get there. And it is my suspicion that you can probably get to topology if we got to something like a Lie algebra or a Poisson algebra or whatever it is, or something like a connection, or some higher order forms of algebra. But this is again my own personal sort of angle to the question: what is, because at the end of the day you're asking the question, what is geometry? What is dynamics? Right? Like what is essential about those things? In my understanding, topology just gives you a framework to define things on top, so that you can observe those features. And I think it's no coincidence that calculus and physics and all these things that you learn in high school and then in year one in university and so on are done before topology, because in a way they were invented without topology. This is also kind of interesting. It's not only the educational path, but it's also the historical path. That calculus was fully invented and fully developed without topology, and manifold theory was invented without topology, right? So it's interesting that the topology came after differential geometry in a way historically, right? So
right.
I don't know. I feel like again, I don't want to overplay this point of view, because it might just be my inexperience with the details, the fine details of topology. But I think a lot of at least the consensus in the community that I've been part of is that topology, sort of technical topology, only really becomes relevant when you go to pathological sort of corners. And maybe the pathological corners might be the very interesting ones, in singularity theory and all these kinds of things. But it might not be representative of what is essential about features of a geometry of space, or the fact that you want to talk about things moving in some kind of space, right? That might be too lean in a way, right?
Right. Okay. So since you bring up coordinate charts, I guess thinking about it this from a very ground level point of view. So it seems like the immediate obvious question is, okay, first of all, is it possible to produce a definition of a manifold for our purposes that does not invoke a notion of local homeomorphism? Or, I guess equivalently, is it possible to develop a notion of local homeomorphism that doesn't require the apparatus of point set topology?
Right. I would say so. I would wager that you can do such a thing. The reason being, a lot of people maybe in the audience will be wondering, like, this guy is just completely fooling himself by thinking that you can do calculus or manifold theory without topology by appealing to the fact that it was defined historically or these kinds of things. I'm obviously not forgetting the fact that once you define manifold theory in this calculus sense, you are inducing a topology. Like that's obvious. There's the fact that topology is there in a technical sense. It's undeniable. But my point is more about the actual structures that you end up with, right? So if you're interested, for example, if you wanted to capture dynamics as the presence of something like directional derivatives, so what you want is something that can be observed to change. So that's your set of observables, and there's something that is moving in space, which is a directional derivative. And in a very abstract sense, as long as you have a ring and a derivation of that ring, you're going to encounter something that morally speaking is is resembling something like dynamics or something like rate of change and velocities and things like that. So that really has no bearing on whether you're in a continuous setting or there's topology or not topology, because it really just means, are you a algebra in the sense, in a vector space with a binary operation that is bilinear, blah blah blah, and do you have this differential rule with that Leibniz rule and linearity and all these kinds of things. That has nothing to do with topology, right? In itself, like it doesn't call to topology directly, right? So I would naturally gravitate towards finding such objects and such constructions directly from this algebraic point of view, which doesn't require topology in an explicit sense. But again, it's just one point of view. It might be that actually understanding how you do topology in a natural way from graphs is going to be much more fruitful.
Right. So in terms of sort of being a bit more concrete about what you're saying in relation. So I think the point you're making, that like obviously it's a general fact that you can manipulate some. It's like how you can use an operating system without really caring about certain details of its underlying instruction set, right? You can manipulate some mathematical object without caring about the fact that it can its low level structure can be parameterized in some particular way, right? You can do analysis with the real numbers without caring that the reals are actually a commutative field or a commutative ring or whatever. Analysis was developed before we even had a notion of what a ring is, and that doesn't particularly matter. The question is, is differential geometry like that in terms of its relationship to point set topology? But I think that's a very important point. In terms of just concretely defining what it is we mean when we say, well, you can reconstruct some kind of topological structure. So my initial hypothesis, and maybe this is stupid, is that it could just be as simple as this, right? You have some graph object. When you take its transitive closure, you are preserving its connectedness information. So in other words, the information about the open sets or the open balls in that space is preserved, but you've thrown away any information about the metric. Any pair of points in the same connected component now have distance 1. So my operational hypothesis has been, and I don't adhere to this very strongly, I'm open to this being wrong, is that the operation of taking a transitive closure is the kind of graph theoretic analog of just passing down to the underlying topological space and effectively throwing away the metric measure structure. And so then, this initial graph, the one that actually does have the metric measure structure, can be obtained by essentially some sparsening of this thing. Sure. And then effectively the space of possible sparsenings is the space of possible metrics that are compatible with this underlying topological space.
I certainly agree with this point of view, and I think it's interesting to spot this part of it. My comment was more generally speaking, would I need an explicit sort of instantiation of what topology means in this context for it to be as a requirement for something like a general theory of discrete dynamics or something like that, or a general theory of, and the answer to that would be no. But I certainly agree that there's something very much like, at least I don't know if topology, but connectivity, because this is another aspect that I didn't, in the desiderata, I talked about proximity, I talked about direction and paths and walks, but obviously there's connectivity, right? I mean, this is getting into, and then you can add to that things like let's call it, I don't know, shape, or not to say something like homology, or I mean technically it would be something more like homology, and sort of homological features of your space basically, which is some kind of higher forms of connectivity and homotopy up to homotopy connectivity, that kind of thing, right? So those, in my opinion, are more topological in nature, but I think, again, those are aspects of space that are typically belong to the field of topology. And I think that here what is kind of playing in the background a little bit for me is that I'm having this sort of a mismatch of use of the term topology as the topology, like the definition of a topology. Sorry, a topology, right? Like one topology on a set, and the field of topology in general, as in like the discipline of topology, right? This is I think it's important to clarify that when I say we don't need to go to topology, or like we can sort of bypass topology. What I mean is the definition of a topology, right, on a set. Obviously, we would have to address and use extensively probably notions that are typically in topology. There are proper topology notions. Limit of proximity. Connectivity and proximity, of course. Yes, they're very similar. Yeah.
Well, I mean, I guess what I'm asking is, so there are kind of two. So you have a topological space with two disconnected components, and then you equip it with a metric, and you compute the distance between points in those two different components. There's kind of one school of thought that says their distance should be infinite, and there's another school of thought that says their distance should be undefined, right? In other words, the distance function is only a partial function; it's not defined if you have points that don't lie in the same connected component. I don't know whether it actually makes any difference which of those two you choose. But if it doesn't, then just saying, well, we can get disconnection is just the limit of what you get as you make the distance between things arbitrarily large. That's one way that we can kind of subsume a fundamental topological notion into a fundamentally metrical notion.
Yeah. No, certainly. I think that is interesting. Again, my mind runs to the concreteness of finding such things, because the implementation, obviously connectivity. Okay, let me put it this way. So graphs, you can understand graphs as essentially just connectivity data structures. And when I say graphs, especially for the audience here, when I say graph, I mean hypergraph in general. If I want to say pairwise graph, I would say pairwise graph. Or in the next 5 minutes, I'm just going to talk about conventional graphs or pairwise graph. I will qualify my statement if I don't mean hypergraph, but I'm gonna save a lot of hypers in my life if I just start saying graph for hypergraphs in general.
Right. And actually, sorry, just on that point, I mean, for the sake of concreteness, in part because the hypergraph packlet that Carlos and Nick have been working on is still under development, I am concretely using graphs for these examples, but nothing that we have said so far is specific to the arity 2 case.
Yeah.
Right. Everything we have said can be extended to hypergraphs of arbitrary arity.
Yeah. What is interesting though there, now that you mentioned that, is I was thinking about it as you were explaining it. One aspect that is not absolutely trivial to generalize is how to go from transitive exactly that we were typing.
Right.
Yeah. Exactly.
That occurred to me as I was saying it. It's like, actually, I'm not entirely sure if that's doable.
Exactly. I think that was a nice confluence of thought. I was going to say just to explain to the audience, what happens here is that when if you have a graph, transitive closure is, there's only one way in which vertices can be connected in a graph. They are non-connected, or they are connected by a pairwise. Like even if you want to have something like weights on your vertices, which you could model as one edges, if you like, those are non-connectivity edges, right? Because they are one edges. But at the moment you have 3 edges or more, what it means to do a transitive closure is very ill-defined in general. So you have, it's not that it's not defined anymore. It's just that you have many choices of what to do, right? So you effectively can the combinatorics of the the combinatorics of adjacency become much bigger, right? And it just so happens that the case of pairwise networks or pairwise graphs happens to be combinatorially one, right? It happens to be that there's the question of for 2 vertices of whether they are connected or not is literally the size of that answer, meaning being 1, is the same as the possibilities of them being connected or not, right? Now, if you ask that for a collection of vertices and you allow for the edges to be of arbitrary order between those edges, those vertices, you can understand that the combinatorics of the answer is much bigger than the nature or the minimal nature of the edge that binds them, right? So it's not obvious, but we're working on it. This is part of the hypergraph backlit sort of research that's going on, and the sort of stuff that I'm doing in sort of my research at the moment is trying to figure out what those generalized transitive closure operations should be like. And I think it is very analogous. So I don't think it really impedes the point that we're making here. And in fact, I would even suggest that we just stay with pairwise graphs for now, just to make it concrete. Because, I mean, if this program makes sense in pairwise graphs, obviously makes sense in the broader hypergraphic setting. But of course, it might need polishing and extension and non-trivial additions to it to make it work in the hypergraph sense. That being said, I do spot a couple of notions that are sort of more naturally hypergraphic than graphic. So, for example, when the measure definition that you gave, right? Sure, you have a so the metric that you have on your, so these are essentially balls, right, around the vertex.
Right.
So, sure, the metric is defined as the shortest path, but in a way, if you are to say, well, the ball around this particular vertex is a graph of things, or is just a collection of vertices, I would say it's just a collection of vertices, and therefore it's a hyperedge of vertices, right? So in a way, what I would say the measure does is really assigning some kind of hypergraph map on top of a graph. I think obviously you need something like a pairwise graph to define a metric in this way, or at least some kind of, you can have a hypergraph, you can project it to a graph. This is something that people in the audience should be aware of. You can project any higher order hypergraph down to a pairwise graph, meaning you basically, probably Jonathan can illustrate quickly, but like you can basically just given a higher order edge, you can just draw all the pairwise connections between the vertices that exist there, right? So that's sort of a reduction that you can always do, and so you can, given an arbitrary, let's say, set hypergraph, you can always define a graph, and therefore you can always define a metric on a hypergraph, right? It's a matter of debate still whether we walk to more general notions of metrics with certain kinds of hypergraphs. But in any case, you do have a sense of metric, you do have a sense of balls, but I think there's really no good reason to take I'm just thinking out loud so there's no good reason, in my opinion, to take a ball, a fixed distance ball in your graph to be a subgraph. I think because, especially if you have a hypergraph to begin with, right, then that pairwise graph that is the ball, sure, it contains all the information of the shortest paths that you can take, but it's more than the shortest paths that you can take from the vertex that you consider, right? Because it shows all the links between the vertices that are contained in the definition of the ball. So in a way, it's including sort of extraneous information for the ball. Like I would be okay with the definition of the ball as the shortest paths from the vertex, right? That's a graph that you have. That's a subgraph, but it only, as I say, it only explicitly includes the paths themselves from the vertex, which is, I think, it's like thinking of a circle or like a disk as the union of the radii to all the points, right? More than, sure, I mean, in set theoretic sense, the disk is also the union of all the intermediate paths between all the points inside. But you can't really tell the difference because it's continuous, right? So that's actually might be an interesting case of where continuous and discrete show some difference. By the way, do you know what I'm trying to say? Because I
do.
Okay.
But I think actually okay. I think you are slightly the thing you just said about the that's a place where discrete and continuous start to disagree. I think you are perhaps slightly hoisting yourself with your own petard with that argument because all right, let me I'm not saying that I actually think this is true, right? But I'm just putting this out there as a crazy idea.
Okay.
That we can shoot down. But so one thing that I wonder, and one of the reasons why I think maybe it does make sense to include both the vertex information and the edge information is to try and make an appropriate discrimination between, say, an open ball and a closed ball, or an open, and more generally, an open set and a non-open set. And what I mean by that is, okay, so if we want to have a kind of robust notion of the distinction between, say, an open ball and a closed ball, then we need to have some notion of a limit point. And a limit point in a purely discrete setting is not obvious to define. And so, okay, my slightly crackpot claim might be that, okay, so what would this look like let's say this is a closed ball. What would it look like if it were an open ball? Well, one possibility is that all the edges are the same, but the kind of the last layer of vertices is removed, right? So when we talk about a limit point, what we're really doing is we're saying there's an edge, there's a binary edge that only has one vertex defined, and the other vertex, one side of the edge is somehow dangling. And then the limit point is the vertex that you would then stick onto the end of that dangling edge to complete it in some sense, right?
Mm-hmm. Yeah.
Okay, if we take this example, I rewrote that was clever of me. I rewrote graph, the vertex graph. Okay, let's take this and okay, crackpot proposal. So let's do that. And we had a random point somewhere, which was this thing here. So, okay, if I say, so we say neighborhood graph, graph 0.3. Okay, so now what we can do, so let's take the edge list of that. All right, so let's first start with the closed case. So this is a closed ball, and we just say highlight. We just do what we did above. Highlight graph, neighborhood graph 0.3, and we style that somehow. No. Okay. But then now what we could do instead is treat the case of an open ball. I'll put this in inverted commas to say that we don't necessarily believe this yet. But so then what we can do is we can say edge list of this neighborhood graph. Let's call that edges. And then we can say vertices is the vertex list. It's neighborhood graph, except we don't want it to actually be the full vertex list. Oh no, we actually want it to be the vertex list of the ball of the previous radius, I think. So then now we can say, well, that's not going to be a valid graph if we try and, so what's the good way of plotting this? Okay, here's what we could do. We could say, I don't know if this will work.
So just to make sure that I understand what you're trying to do. So are you trying to show the edges but not the vertices in the open one?
I'm trying to show the edges but not the final layer.
The final layer.
Exactly. Yeah, exactly.
All right. Yeah.
So if I do that, okay, but then I also want to do style, and then I actually so then actually what I want is complement of this comma this, I think. And then I say style. I don't know if this works because I can't remember the order of operations for that. Directive, let's do green. Okay. All right. Well, it's hit a boundary there, which is maybe not so informative. But okay, so what I'm trying to do here is to show. So this is the complete closed ball,
Mm-hmm.
and then everything that's in pure red is the open ball, and then the green points are the ones that are that were in the closed ball but aren't in the open ball. So these would be like the analogs of the limit points.
Mm.
And so in this set, if this were your setup, then I would say you need both. You need the edge information and you need the vertex information, because the edges the edges that have like orphaned vertices
Yeah.
are the things that define your limit points, right?
No, for sure. No, I agree. I would say I agree with including edge information.
Yeah.
And I think this is I was, as you were making this, I was thinking that this is actually an interesting way of addressing the notion of continuity the notion of directionality, right? Like this idea of direction in topology, which is, in a ball, as I said, a ball really is the union of all the radii, right?
Right.
But it's also the union of all the subsets of the ball, and because it's this continuum, and it's in particular infinite number of balls inside, right? So the distinction between the open and closed is really, whether you are including the endpoint of your radius or not in that
Right.
in that union. So I completely agree on there being edge information in the ball. I think that's clear. I think even that most people think of balls as being sets of limited distance, like up to this amount. I think it might be interesting to bring into the discrete context to think of them as unions of radii, right? In a way, because that's effectively what you're doing here, right? Like you're saying,
Right.
you're finite in a finitary way. You're saying, fly out of this vertex with this amount of fuel, right? And
Right.
get as far as you can, but with this finite amount of fuel. So the places where you land are the closed ball boundary, and the place that you cover are the vertex set of your ball. My point is that edge information is important because it might simply tell you, boundary or no boundary, which is exactly what it is in topology, right? Like closed boundary, open no boundary, in at least in the context of balls, right?
Right.
Yeah, and so that's why I was, instead of representing all the edges between the vertices, I would maybe just represent the paths from the vertex.
Right. Okay. Sorry. I am attempting to illustrate the point that you're making. No, that was a bad idea. All right. Okay. So that's radius 1. That's all the points at radius 1. That's all the points at radius 2.
Yeah.
If we went up to radius 3, we would get up to there. And so then the point that you're making is, if we take this and we take a union of all of those, so actually we can do that just by catenating, and then we do subgraph.
Yeah.
We get the induced subgraph of that. Then that should be the same as if we just took the straight up ball. Wait, 3. Okay, it's not quite the same, but it should have the same vertex list at least, which we should be able to check. Otherwise, I've screwed something up. Okay, no, it doesn't have the same vertex list. What did I do wrong?
Yeah, well, you find that I will address this question in the chat.
Yeah, sure. Yeah, go
it's
on.
entirely relevant to what we're saying. So they're asking, how would the set with an edge but not the vertex look like? And how would a walk on an open graph look like? So the crucial point here is that vertices and edges, these are all different bits of information, right? So a hypergraph is a collection of vertices and then the edge structure on top of them. And so you could even say that to be perhaps proper, in my opinion, the structure of you have a graph. Imagine the graph on the screen, right? Like you have some basic graph, the blue stuff, right? And that is and so the information of that graph really is the number of vertices have like memory slots where you can place stuff. They are like symbols or like elements in your hypergraph, and then you populate them. And so you can imagine that there's infinitely many such memory slots, or like arbitrarily many of such things. And then the ones you're populating, these are the ones that characterize your graph, right? So the vertices you could think of as some default one edge on them, and then the two edges are highlighting the two edges with a particular combinatorial structure, and so on in higher edges. So when you specify something like the distinction between a closed ball and an open ball would be that you specify a set of one edges, which is the points within the ball, and then you specify a set of two edges, which is as we are discussing here, either all the paths between them or the paths from the vertex that is at the center of the ball, or things like that, right? So the idea is that and then you specify the 3 edges and 4 edges and so on. 4 edges and 3 edges are not a thing here, so they're just an empty set. But the idea is that you're specifying sort of graphic data on the underlying vertices, and you can see highlighted vertices as one edges if you like, and so that way you have this very sort of parsimonious way of addressing that question, which is I just specify edge information, edge data on top of my graph. So that's why it's not weird to think that you have a set of one edges, which is all the points in the open one, which is the weird one that you refer to, right? So the open one would be you have all the vertices highlighted, and you can think of them as one edges, and then you have the set of two edges happen to include all of them in their pairs, but they also have ones that are pointing outwards to the layer of distance 3 vertices, right? And so those two edges are in the set, right? It's not necessarily problematic there.
Whatever. There's some weird out by one error. I can't bother to track it down, but
Sure.
it's the underlying point is the same, right?
Absolutely. But I think this is an important. This might be actually very, very relevant for future developments of this program, right? But would you agree that it makes more sense for a ball to have a center? Because then the other thing that you miss in the information there is that obviously we haven't talked about directed or undirected. I think that's an interesting thing to bring in at this point. But I would say that a ball should remember where the center is, right? And I think one obvious way to do that, just at the level of the structure, obviously it doesn't characterize the center, but it is a matter of memory of the center, is that the edges the edge data that you carry in the ball are the paths from the center, right?
Right. Okay, so here's a quasi philosophical question.
Yeah.
What, if any, do you think is the relationship between memory of the center of the ball and the distinction between affine and non-affine geometry?
Exactly. Yeah, that's a great point. So my understanding is that to do conventional affine geometry, right? Okay, let me answer it more philosophically. You ask philosophically, then I'll answer philosophically. So philosophically, the distinction is you're doing undirected graphs or you're doing directed graphs, basically.
Right.
So if you are able to, I would say something like, there's very broad strokes. It's obviously that's not an answer, but I would say that's exactly, a binary edge, so a pairwise edge that is undirected, that very much looks like an affine distance in a way. It's basically, by affine distance, I mean this is the statement that these 2 points are not the same, right?
Right.
But if you have a directed edge from two vertices, that obviously contains a statement that these 2 points are not the same, but then obviously also has the statement that this point is pointing towards this other point, right? It has I mean, I'm stating a completely obvious thing. It's not. I'm not trying to make any deep statements here, but I'm glad that you mentioned that, because I was going to mention that it might be that you have a undirected graph as space. I think I like that as your background. In the same way that I like undirected hypergraphs in general as space models, right? I don't think, why should there be an intrinsic ordering of the atoms of space or whatever we want to call them, right? Like, it makes intuitively it doesn't sit right. But once you traverse that space, then the directionality is induced, and that's basically the entire game of, in my opinion, the entire game of calculus. And that's actually the way I used to teach it in an unconventional way, was to begin with affine spaces, begin with sort of abstract sets where there's no sense of center or origin or anything like that, and then learn some linear algebra, some maps from vector spaces to vector spaces, and you do functions from vector spaces to vector spaces, and then you do derivatives and all that machinery you build on vector spaces. And then you go to an affine space and you say, all right, so I can point my finger to this place in a affine space, and as long as I have the structure of an affine space, which is basically that you have a one-to-one map to vectors in some model vector space, then you can bring all the machinery about derivatives and about functions and about calculus and all that stuff, right? So the analogous situation here, I would claim, is that you have some graphic structure that is basically undirected, right? Some hypergraph or graph like we had here. And then you put your finger on a place, which is a vertex maybe, right? And you place yourself at a vertex, and you start to say, okay, how can I travel away from here, right? And that's basically the leading to the definition of ball, which is some aggregate of answers to that question, right? How can I fly away from here? And all the questions of differential calculus in some way are going to be condensed in the maybe like one step, two step kind of constructions. It would probably be some kind of statistical measure over certain number of balls around the point, right? To compute sort of statistical derivatives or statistical statistical rates of change or things like that. But I would say the crucial aspect there is going to be that on top of an undirected graph, you're going to build directed graphs, right? You're going to be and the interplay between them is going to be in my intuition is going to be similar to the interplay between just the background affine intrinsic manifold points with the algebra of derivatives that happens more at the level of maybe coordinates that people like to see that, or vector space, model vector space, or something like that, right? So that's my intuition at the moment. So I think we will only really see these patterns when we are treating undirected graphs and directed graphs in this interplay, and sort of because I think the analogy is very straightforward. It might not work. It might just fail to really pan out. But the analogy seems very strong. And it might be fooled just by the fact that you're represented with an arrow. It's like
right.
I mean, I'm actually not going there. I'm not saying that I am being the analogy is suggested by the fact that we're represented with an arrow. It really is suggested, in my opinion, by the fact that how you get differential calculus from something that looks like an affine space is precisely by defining what a curve is. And you have to begin with the notion of curve to then define the notion of function, to then define the notion of infinitesimal change or something like that. So to me, those can only be paths which are some form of directed subgraphs in an undirected graph, right?
Right. Okay, so here's a question. So what is the relationship, if any, between directedness and torsion? So my reason for asking that is, okay, so if we have, I should come up with better names for things than just graph, but whatever. We have some random graph, let's make it a little bit more dense. Then, so this is by default undirected. I can make it directed, and so now it will have a pair of directed edges for each previous undirected edge. And okay, if I now imagine that this thing has edge weights, so let's get vertex labels. Oh no, I want edge labels. Okay, so these are all edge weight 1. I could then imagine saying, okay, well, we can imagine now having we don't just do the standard path length, we use the weighted path length in the graph. So now if I compute a path distance between any pair of points in this graph and a path distance between any pair of points in this graph, I get the same answer, right? Sort of trivially. But if I now tweaked this so that half of the, for each pair of vertices, one of these weights was 1 and one of these weights was 0, then now I have I have something which now acts like, its combinatorial metric acts like a directed graph metric, right? It's a way of getting a directed graph, out of that. But in so doing, all we've done is we've just said, well, the metric distance between point A and point B is just, it's the most different it can be from the metric distance from point B to point A. It's kind of it's somehow a limiting case of a torsion metric. So the reason me asking the question is it reasonable to think of directedness in graphs as being a limit of maximal torsion?
I want to fully understand what you're asking. So,
sure.
What do you mean by torsion metric here?
So, as in in the differential geometric sense, so a metric where the contortion tensor is non-zero.
But I think what you're breaking is the symmetry of the metric, right?
But if you have a non-zero contortion tensor, then you have an asymmetric metric, right?
But is it a metric then? I mean, I'm a bit confused, but because I mean, if you as you said, I mean, you take this graph and then randomly delete some directed edges, right? So you no longer have this sort of symmetry of paths, right?
Right.
I mean, what it's obvious that I can see is happening is that you're modifying the commutativity of the metric distance. And I don't want to say the metric tensor would be metric tensor, but
exactly.
But the symmetry of the is that right? Is that?
Yeah. Exactly.
Okay. So I'm unfamiliar actually with that situation because I mean, as I understand it, you're changing. My understanding of this is if this is what you say your space is, right? Then it stops to look like a manifold in the usual sense. Because that's like to say that if you can go from in a curve, in an embedded one dimensional manifold from A to B, you cannot go from B to A, right?
Right, but okay, but this is again why I brought up this relationship between connectivity and proximity. So here's the sort of model I have in mind, right? So
right.
So
no, I think I'm starting to see what you mean. Yeah.
When we do this construction where we've got we imagine every edge as being every undirected edge we model as a pair of directed edges going in either direction with the same weight. Okay. Mm-hmm. The fact so. Here's my hypothesis, right? That the assignment of weights to these directed edges is the imposition of a connection. So when we say that all the weights are the same, that the weight, in particular, if we have a pair of adjacent vertices, the weight of the edge from A to B is the same as the weight of the edge from B to A. That's equivalent to doing a Levi-Civita connection. That's so we have some unique. There is a unique, just as there is a unique torsion-free metric compatible connection on a Riemannian manifold, there is a unique assignment of edge weights that gives you zero torsion of the resulting graph. But we can imagine now the case where they are not symmetrical, and therefore in general where the distance between 2 points is not the metric distance is not a symmetric operator, is not a commutative operation. And so what I'm asking is, if we take the limit of that, where now the distance from A to B is some finite number, but the distance from B to A is infinity, effectively, that's now giving us like a sort of manifold-like model for something that acts more like a directed graph. That's sort of my claim.
Yeah. No, I'm starting to see what you mean, and I guess so because so effectively, it's the commutativity of paths for geodesics, right?
Exactly.
Right.
This is okay. So first point, connections as assignments of edge and therefore path weights. So this is the analog of Levi-Civita. But then if we wanted a more general, say, affine connection or something, then I guess what we would do is we take this, we would do that or something. Okay. So now this is also a metric space, right? If I can, for any pair of points, I can assign a metric distance. I take the shortest path and I count I sum the edge weights just as I did in this particular instance. But now that operation is not guaranteed to be symmetric. The distance from A to B will not in general be the distance from B to A. And so my claim is that this is the analog.
Yeah.
So this is like the Levi-Civita case, and yeah, this is like general metric affine connection.
Mm.
And then, as I say, the thing if this is a good way of thinking about it, or a reasonable way of thinking about it, the thing I like about that is that it means that we can treat, as I say, we can treat directed graphs as just a special case of like extremely as an extreme case of a torsion connection.
Yeah, I like that. I think I'm starting to see but you will still agree that there's an underlying undirected graph sitting in the background, right? Yeah.
Exactly. That's what. So that's why I'm. So in my proposal for how we might decompose this, we in a sense, okay, this is the problem with the fact that we, in the standard setup of differential geometry, there's so much freedom, right? You have. You have freedom to assign a metric, you have freedom to assign, a contortion tensor, you have freedom to assign a non-metricity tensor, you have freedom to assign curvature, and then there are these various theorems that say that you can kind of, you can simulate one of these with the others and blah, and etc. It's a hugely overdetermined system somehow. So I guess what I'm arguing is maybe a way to think about this would be to say, okay, well, the actual combinatorial graphs, structure of the graph, that's like our choice of metric, right? So we got a vertex list. That's our underlying, that's our set of points. That's the, that's the collection of points that form our topological space. Then the transitive closure is at least the connectivity properties of the topological space. The graph itself, or the combinatorial structure of the graph, that's like our choice of metric. And then the choice of edge weights on top of that graph, that's like our choice of connection. And so everything we've been doing so far has been assuming that, in a sense, if we think of the underlying data structure not as being this, but as being something like this, then everything we've been doing so far has been assuming that the edge weights are all one in both directions. So we've been assuming Levi-Civita.
Wait. So let me say that again. So you say that the distribution of, so from the edge distribution, is the edge distribution itself similar to a metric structure? You're saying?
That's what I'm wondering, right?
Okay. Because I can clearly see the analogy where once you have a directed graph, right? I can clearly see that the distribution of weights is analogous to a connection, right? I can clearly see that. I'm just. I mean, I guess it makes sense to think that one particular graphic structure corresponds. I mean, it does determine a metric, right? So, yeah, actually, that makes sense. Yeah, I mean, I'm just like
I know I
observing it real time. Sorry.
I don't want to. I'm not trying to be too dogmatic about this.
No, for sure. I'm just
as a possible decomposition.
No. I completely see the point. I think, and it's actually it's a nice picture. I mean, I think it gives us a lot of homework to think of the hypergraphic case, but that's actually
yes, that's
actually
true.
relevant to one of the contents of this live stream that we discussed in our call, in a prior call previously, which is how do we generalize this notions of tensors and so on in geometry to higher order objects, right?
Right.
So I find this beautiful because we've just by really restricting ourselves to the graphic case, we are prompted with a natural sort of path into higher order by considering hypergraphs. Anyway, this is besides the point. What I'm trying to say is, yes, I'm starting to see quite clearly that having a vertex set as analogous to your space, intrinsic space, so to speak, space of points or set of points, and then having graph structures on top as being effectively metric structures, and then it makes sense to have like a directed or weighted directed graphic structure on top as a connection, because that also recovers the intuitive notion of a connection in the way of it's how you can move around your manifold, right? So
exactly.
So in a way, that's what I wanted to say earlier is that graph over there, maybe not that one, but maybe the symmetrically weighted one,
right.
That one is the graph of which all the paths are going to be a subgraph, right?
Right, exactly.
So yeah, and so it's interesting to see it that way. I mean, because you, as you say, rightly point out, you can change it. Sorry, I'm just basically rephrasing what you said, but like this is me understanding exactly what you're saying. But exactly, you can change the graph or the weights, as you said, right? And therefore, yeah, as you say, it's a metric. Yeah, you could change the graph entirely, and then you would have a connection that is just not metric, right?
Right.
Because it doesn't talk to the metric, because it's just connecting points that were unconnected by the metric structure that is the undirected graph underneath, right? But the fact that you are effectively covering it, it makes it metric, right? Is that intuition correct?
That's how and let's make a note of that the fact that the edge weights respect, I guess, the underlying graph connectivity.
Exactly. Yeah.
Is somehow, that's related to metric compatibility of the connection.
That's very cool, actually. That really, I mean, the dictionary, it starts to form in my mind. I don't know if this is actually going to be rigorously proven at some point, but the dictionary starts to make sense in my mind.
Right. Yeah. So I guess what as you say, there's a couple of homework items. So one is obviously how does this work for hypergraphs?
Oh yeah, that's a big one.
But also I think so this is, as you say, we are successfully capturing kind of one aspect of what a connection is, the thing that lets you sort of somehow move around. But so how do parallel transport, covariant differentiation, etc.
Yeah.
Or I get distortion of basis vectors, etc. work in this setup? That's not obvious, but
well, I would say covariant differentiation is almost obvious to me.
Okay.
So for covariant differentiation, and this is going back to what I said earlier, like the notion of a derivative, I mean, if I think about this for 2 minutes live, I think I might be able to give you the answer.
Let's just do it with live science. That's what we're about.
Yeah, exactly. So let me just basically make sure there's I don't think there's any impending question from the audience, but so let me just okay. So if I believe the picture that has formed in my mind the last hour or so, then the vertex set is your underlying space. Therefore, functions are literally functions on that set, right? I'm just gonna run with that because it's super easy.
Sure.
So function space is just vertex to whatever. What do we need? You need to evaluate on some ring, basically. It doesn't matter you could even have it Boolean or something very similar, like, or not Boolean, but like the smallest ring or something. Doesn't matter. And then it is the case that obviously if you're valued on a ring, then the set of functions valued on a ring is itself a ring. So we're good there. And then all we have to do is to find what, if I specify two pieces of data, which is a vertex, which is a point, and something that is going to be analogous to a tangent vector, then those two pieces of data, given a function, will give me another function. Sorry, will give me a value at that point. So it will give me effectively, if I had that data specified for all vertices, then it will give me a new function, right? So that's the notion of a directional derivative. It's not yet the covariant one, but we'll get there.
Yeah, sure.
So, okay. I mean, what is a tangent vector? I mean, obviously it's a directed edge, right? I mean, you're going to use the arrow argument here,
right?
So I mean, it's like, so okay, so what do? You take a difference, right? Like, I mean, it's as simple as that, I think. Like, you have a function, so you have a value for each vertex, right? Then you have two vertices, you have a directed edge between them. So that directed edge tells you that you're going from this value of the function to that value of the function. So what is the derivative measuring? The rate of change. So you just literally take endpoint minus starting point, right?
Yeah, so we just basically do a finite difference definition.
Correct. Of the
derivative along a directed edge.
Yeah. And I guess...
So that would be a directional derivative.
I would say so, right? It's as simple as that. Yeah. And then the question is, okay, so the reason, I mean, for this to be called, so far it's obvious that that's a rate of change analog, some kind of discrete rate of change analog, that's clear. But to call this a differentiation, we just have to check Leibniz rule. That's basically the only piece of homework we have. And
right.
So that just might be completely trivial arithmetic at this point. So if you have two functions and they evaluate to the product, all you have to ask is, what do you evaluate the finite difference to? I don't know. I need to write down something. Give me a second.
Yeah, but also, I mean, at this point, it doesn't even matter that it's a graph, right? Like, we're not using...
Not yet. But I mean, the idea is that for this to be like the derivation property will show up locally, but the whole point is that when you define these things globally, then a vector field is just going to be a particular directed graph on top of your because if you're saying that tangent vectors are directed edges, right? A vector field is going to be some sub-directed graph or something, right? Like it's going to have, it's going to be it's similar to how in fine geometry, your tangent vectors are actual segments of your space, right?
Right.
Like obviously, for people who are familiar with differential geometry, we put all the vector information on some Platonic parallel universe, and technically they never touch, right? Like, although we always call them tangent planes, like technically they never touch. It is the case, I think, here that we're gonna have that same sort of story where you have the underlying graph, and on top you have this directed graph. And I think the most simple way to think of that is as directed edges, because at the end of the day, tangent vectors are sort of like infinitesimal paths, right? So infinitesimal here can only mean one-step paths, right?
Right. But here's a question, right? So it's which is a lot like the question about, can we just jump straight to differential geometry without having to traverse, the interstices of point set topology?
Yeah.
Can we, for instance, can we jump directly to defining a vector field without intermediately defining tangent bundles and spaces of smooth sections of tangent bundles and those kinds of things?
I would say so. I mean, I was saying vector field as in, tangent bundle just trivially, Like I was defining effectively the tangent space at a point, right?
Right.
And
Yes, but your definition, as I understand it, your definition of the tangent space at a point is literally just the neighborhood graph of distance one, right?
yeah,
Yeah.
yeah.
So the
I mean,
tangent bundle is just the collection of all geodesic balls of radius one.
exactly.
The disjoint union of
Disjoint union of, yes, yeah, exactly. Yeah. I mean, as I said, I was using the arrow argument, so it's not a very strong, sound mathematical proof. But
well, no, but I like this. Let's go with that.
So let me just I don't know if you want to code on something, but I just need 30 seconds to do a
Sure. No, I'll in the interest of not having dead time, well, I'll vamp, but
yeah.
You work out the Leibniz rule. Or
Yeah. I'm just I'm gonna compute something very quickly.
Okay, so let's okay, let's make it clear this is an operational idea. Okay, so we've got graph and let's do the tangent space at a point. We can do neighborhood graph. All right, so I'm just selecting a point and getting the neighborhood graph. It's one. Oh, we want this to be the directed graph version, I guess, in the interests of making the arrow argument make sense. So I take style neighborhood graph, directed red thick or something, and we'll say style 1. So we'll style the vertex specifically as green. Okay, so we've selected a vertex and we've got that's not ideal. Neighborhood graph doesn't respect directness in that way. Okay, but that's all right. We can fix that probably. How do we do that? Oh, we don't need neighborhood graph, right? We just need we can just do vertex out components. So we do vertex out component. Oh God, what's the right way to do this? I mean, we could be incredibly hacky and just do directed edge 1 hash, and then map over that, but dropping the first, I guess. No, dropping that. I mean, that's a horrifying way to do it, but okay, there we go. There's a hacky approach. But so that gives us a tangent space at a point. At the point in green. And then now, if we wanted to obtain the tangent bundle, then the idea would be we just literally take that, we quantify over the points. So now instead of 1 here, we say point. Over the vertex graph. Okay, so then that gives us that. And so, is it worth? Tangent bundle of the entire graph. So if I say highlight graph of that. So now, the tangent bundle is just the disjoint union of all of these. So it's like effectively the equivalent of this list. So if I say highlight graph of that and I do style of this thing, well, actually, no, if I just do that, I think it will highlight each one in a different color. There we go. I don't know if that's a useful graphic or not, but that's some graphical indication of a tangent bundle. So each individual tangent space in the bundle is highlighted in a different color. And so then the space of possible vector fields that we could define over this graph would then be whatever the analog of the space of smooth sections of this bundle is, which I don't immediately know. But once Collis is extricated, we will ask him.
I'm almost done.
No, that's all right. Meanwhile, okay, so what else could I talk about? I mean, there are several things that we kind of skipped over. Okay, one thing we could do, one thing I could just mention is I'll briefly kind of do a shout out to Carlos's main research project, which is this sort of higher arity stuff and why it's relevant to this. So this was briefly mentioned before when we were talking about the higher arity generalizations or hypergraph generalization of transitive closure. So one thing that those of you who followed Carlos's work are probably aware of, but others of you may not be aware of, is that there's this very interesting and it seems rather deep connection between transitive closure in graphs and the notion of associativity in algebra. So to explain what I mean by that, if I take a directed graph in the form of a quiver, so sorry, so I do okay, so if I have this. And then I construct a category from it. So, which I do just effectively by taking a generalized transitive closure of this directed graph. Then okay, so now we have this composition. This edge, the G compose F edge, has been introduced by a transitive closure operation. But now, if I introduce a third edge here, if I do W like that, so now my transitive closure looks like this. But now, of course, there are two different. When I transitively close this thing, there are two different ways to get from X to W. We're only showing one of them, but internally we can say, if I say associativity equations, we can see there's actually an H compose G compose F and there's an H compose G compose F. And the statement that those are the same and that therefore this is a graph and not a multigraph is the statement that associativity holds. So somehow there are these, associativity of morphism composition follows directly from the statement that somehow the transitive closure is unique. And so the property of associativity in algebraic structures is somehow deeply connected to this operation of taking transitive closures in graphs. And so my suspicion is, although Carlos is the expert, that somehow, whatever the hypergraph analog of transitive closure will be in some way deeply related to the sort of the higher arity versions of associativity that Carlos and other people have been studying. Is that a fair characterization?
Yeah, I would say so. Yeah.
Okay, cool. And how are things? How's Leibniz?
It's not working out.
Okay.
So let me just show this for a second on the live stream.
Do you want to share screen or?
Yeah.
Sure.
I'll just share very briefly. This is a very embarrassing computation because it's literally just arithmetic. Okay, but so you can see this here. Yeah. So my definition of function is evaluate the vertex set V on some field F, where you can do addition, multiplication, and you have your lovely distributivity property. Then take some point on your vertex set. And then, okay, let me see. So P and Q are two vertex. Maybe I'll talk over it in case you see some obvious mistake here, but I don't think it works out with the trivial finite difference kind of definition. And then, so you specify a point P, that's the sort of center of your derivative, and then you specify a tangent vector, which is just specifying a directed edge. So that's kind of on the graph, right? And so, okay, so what is the directional derivative? So it has the information, you have to provide the information of a point and a tangent vector. In this case, because the tangent vector already has the information of the point, I don't need to specify more. So I write it like this: PQ, the vector going from P to Q of the function f is defined as difference of f at Q and f at P, right? No mysteries there. So the directional derivative of the product of these two functions, obviously you can do the point-wise product of functions, right? So, and they are defined by taking the value there. So you do that definition as above in this way, right? Fg at Q, Fg at P, and take the difference. And now you compare it to what would be the Leibniz rule for that, which would be F evaluated at P with the derivative of G evaluated at P and the derivative of F and so on. and you just write it out, and it doesn't quite match. So things don't cancel out nicely.
So my okay, this is going back to like whatever undergraduate first year analysis. Was like my recollection of the proof of the Leibniz rule for just standard real analysis is it involves this like there's this slightly Jedi thing that gets done a lot in real analysis proofs, right? Where you add something and then you take it away again.
Yeah,
and then
I think that might be.
But then there is like a residual term, as I recall, I think, in the numerator that then but that has a like a dx, it has a delta x dependence that then vanishes in the limit. So what I suspect is happening, well, I know what I guess is happening is you're getting something that whatever the residual thing that you've got left over is the thing that if we were doing this whole thing over a delta x and then taking the limit as delta x went to 0, that would be the thing that would be.
No, I was exactly thinking of that. So yeah, I mean, the hope was that there was some. I mean, maybe there's. What's interesting here is that maybe if we're going discrete, we go discrete all the way in some sense. So we also go discrete on the field, where we are evaluating things. And so maybe you want to use some kind of rather exotic behavior of your field, so that it amounts to that behavior that you're referring to. Right?
So when we've got binary graphs, we're basically operating in F2, right? I mean,
sure.
So if it's a characteristic 2, then a bunch of stuff is going to disappear. Yeah. Is the stuff that's going to disappear the right stuff, so to speak?
Yeah, I mean,
okay.
So actually, this is an important point. So before getting lost in the, so I don't need to show this any longer for now. I mean, I think it was a good conversation started for this point, which is the choice of the real numbers as the field in differential geometry. I've always seen as okay because your model space is a real vector space, or it's a finite dimensional vector space, or your model space is literally Rm, right? Similarly, if you choose the complex numbers as your model space and you do complex analysis and you have this sort of like, like complex geometry and things like that. But so the question here is, if we begin with a graph, I mean, you said F2, right? It might be that's right, but I feel like, is that really the? I guess it might be, right? But in a way, how? I'm striving to see how F2 sort of gives you R in the limit, right? In some sense.
Yeah, it's a good question. I mean, in a trivial sense, it very obviously doesn't.
So F2, just for concreteness, is 0 and 1 with the Boolean algebra thing, right?
Right.
Yeah.
Right. So my reasoning, okay, I literally just said that. I didn't, like the words came out of my mouth. I didn't really have any reason. So let's think it through.
So.
Oh yeah, sorry.
No, I mean, just an intuitive point is that I guess you could, because I see F2 as this like the basic Boolean algebra, right? So right. In a way, it's like the binary questions. Right? It's like asking the binary questions, and so
yeah. So my sort of proto reasoning was okay. So
right.
Let's run with the analogy that the underlying graph structure is like the metric. So how do you generate the graph structure for an RT2, for an RT2 hypergraph, i.e. a regular, an ordinary graph?
Yeah.
Well, you take any pair of vertices and you ask a binary question: are they connected by an edge or are they not?
Correct. Yeah.
So the analogous thing in metrical geometry would be, you take a pair of points, I guess, and then you define some projection of your metric tensor. You take you take a u and you take a v and you define the projection. G mu nu u mu v nu. And that projection is typically defined over the reals. And the question is that Is that a good enough analogy to make any sense? Probably not.
I think it's a good analogy. I was thinking also of that. Yeah, that's actually an interesting. But nonetheless, the metric distance, here is valued in n, I guess, right?
Yes, except so here's my okay, right. Actually, now it's a good time to share screen again.
Yeah,
So let me just check. So this is what I think is the translation of your idea, right? So this is a tangent. This is the tangent space at the green point. Is that?
Yep.
Is that fair? And then this would be I mean, this is like a very way of illustrating a tangent bundle.
That's cool.
But so okay, so if we look at this, right? So we evaluate the metric tensor at this point. Well, of course, we can only ask about metric distances within that tangent space, so to speak, right? Like we don't get to ask the distance between this point and this point. We can only ask the distance between this point and any one of these points.
That's right.
So the only possible valuations are 0 and 1.
Okay.
And whereas so analogously or the analogous thing in differential geometry would be you evaluate the metric tensor at a point, and then you're only sort of allowed to ask about projections of the metric tensor, to infinitesimal, along infinitesimal line segments or something. It's just in this case, infinitesimal line segments are just edges that have, length exactly 1.
Okay.
I don't know if that. I mean, that's I'm not entirely.
That makes sense. I like that. It's just so then it's a very concrete question now. Does I mean this is just a very finite question, very small finite question of is the Leibniz rule always true in F2?
Right.
Because with finite difference derivative.
And if it is, then that hints immediately at something that's very interesting, which is that the Leibniz rule is different for hypergraphs, potentially, right? That there are that there could be additional terms in the Leibniz rule that emerge once you go to higher arity edges.
Oh, that's very cool. So I'm sure this has been done. So I'm just literally going to Google derivation.
Yeah, this is your this is your thing.
Oh no, that was a very bad search. Derivations of the F2.
Okay, so let's note this down. So like claim. Actually, I'll load it down here. So we evaluate the metric tensor at the green point. We can then ask about metric distances between points in the tangent space.
Okay. So I have some interesting properties. Okay, so
by red edges. In the discrete case, unlike the continuous case, these distances are either 0 or 1, i.e. elements of F2. Claim. Therefore, R, the codomain of the metric tensor projections, differential geometry can somehow be recovered. Therefore, some property of R can therefore be recovered as a limit of collections of properties of F2. I don't even know how to formulate this conjecture in a vaguely precise way, but I think that's kind of intuitively that's what we're trying to assess whether this is reasonable, right? We're somehow trying to ask. We have a bunch of these local tangent spaces, a bunch of these tangent spaces, these discrete tangent spaces that are just neighborhood graphs of radius 1, So the value of the metric tensor in any one of those tangent, evaluated at any one of those points, those valuations come from are all elements of F2. And so then the question is, does this behave enough like the continuum metric tensor which has its valuations in R, that in some way some essential features of R can be reconstructed from limits of just a bunch of F2s that are kind of stitched together in this way.
Okay, I have very good news.
Oh yeah, okay, it disappears.
It works. This is really cool, actually. I'll share the screen in a second.
Yeah.
This is really cool.
Well, yeah. Let me know when you want to share the screen. But let's make.
I'll share in like a minute. I'm just writing it so that people can see.
Yeah, great. Okay, so important point. Exciting claim. In F2, the boundary. I don't know what to call these things. The boundary terms vanish in the Leibniz rule, i.e.
Okay, this is very exciting now. I'm getting properly excited.
i.e. the Leibniz rule actually holds. So extension claim, perhaps the Leibniz rule is modified for higher arity hypergraphs. Okay, so why would this be true? Why? Because it may be that the vanishing of these terms, let's not say it may be, it is highly likely that the vanishing of these terms is peculiar to F2 and some subset of the set of finite fields.
Yeah.
Not a property of finite fields in general. Which, I mean, I'm speaking out of turn here because I'm this is your area, not mine. But like, does that not potentially have implications for the whole business of higher Lie algebras and things?
It does. That's also why I'm getting excited, because it definitely, yeah. Okay, so let me share the screen briefly to bring closure to this question. This is very cool.
Exciting. Oh, hang on, wait. Stop share. There we go.
So this is super amazing. Okay, so anyway, back to the drawing board, literally. Oops, wait. So we had this question, right? So if we define the finite difference as a, so I don't need to change anything, right? Like the definition made sense, right? So you have to make sense of this formula, whether the finite difference of the directional derivative so defined as a pointed finite difference, let's say, right? If it matches this equality, right? Evaluating the pointed finite difference of the product is the same as evaluating the addition of one evaluation and the finite difference of the other plus the other and the other, right? So this was not the case in general. Like you can see, just arithmetically, that's not gonna, as you said, like it's exactly the same computation you do when you prove the Leibniz property for calculus, right? In derivatives, in that case, it's super interesting to see that when you go into the infinite field case, where you have this the properties of the reals, that you can like take limits and push things to vanish, right? Some vanishing property at the end of the day, right? What you do with limits in calculus is that you have some way of generating zeros, right? You can get plus zero in some formula so that your two expressions match, right? So interestingly, we can do the same thing here, instead of by doing some limit mambo jumbo, right? By being so small, like the limit is like you're so big that you can sort of like go so far that things become so small. Here you're so small already that things vanish out. So the way it happens is when you're in F2, those two, so let's take the step that F is F2 now. So those two equations are true in F2. That's what makes F2 special, right? That's very, I mean, you could just go case by case and show that this is true because it's such a small field. Like it's not such a difficult, but it's actually very nice to just show that, I have that expression, x plus x is always 0, so that means that any term is equal to minus itself, and I can cancel any pairs of of terms that appear. So obviously, this is the same as that one, right? So they disappear. So that's applying A. No, what I'm saying, applying B. No, applying A again. So, and the fact that each term is equal to minus itself just allows me to write this formula. Obviously, other formulas are true, but this one in particular, right? So, very excitingly, this matches, right? So when you define, this is super cool. So when you define functions to be the taking values over f2, or at least any field with those properties in general, I guess. I don't know how many of those there will be, but you're getting derivation property. You're getting the actual the rule works. So this, I mean, I am now confident to make the statement. Like I don't have any hesitations to say that when you define a vector field to be just a distribution of such things, that's a Lie algebra. That's it. There's no qualifications to be made. I mean, it is literally a Lie algebra, and so yes, indeed, when we think of how this extends to when you assume that your metric structure is based on ternary edges, then yeah, you can, yeah, these questions open up, and we don't know what's gonna happen. So that's super cool. Yeah, very glad that we pushed ourselves to consider F2, because and as you said, I think it makes perfect sense intuitively in the picture that you were drawing in your notes. I think that makes perfect sense. And I like very much the idea that where you can, I mean, from F2 you can obviously get n constructively by accumulation, right? And that's also very, I mean, it's kind of a more philosophical point. Perhaps people in the audience would appreciate having a bit more of a philosophical point, because instead of me just struggling through basic arithmetic, but yeah, I think that you can imagine that a vertex is some kind of minimal bit of information, right? And so if I had neighbors that are connected, the only information that you have is, do you stay where you are or do you travel, right? And so that binary, that sort of Boolean value, that sort of F2 value, 0 or 1, is effectively measuring that, which is exactly what a vector carries, right? It's either you travel or you don't travel. So when you travel, you have these sort of proto functions that are in the same way that you're considering the minimal vectors to be just steps between vertices. The minimal functions are the ones that are just telling you there's nothing or there's something, right? Like it can get more granular than that. And then when you travel, then you can start to sort of define aggregates of things like path length, right? Which you're basically but what I'm trying to get at is that you do it, you get those things almost when in a constructive way, like mathematically in a constructivist perspective, right? You are if you don't know about, if literally all you know about is a universe of points and arrows, like or points and links and paths in between those links, then as you said, it's a very binary world, right? Like it's a world made of just topological pairwise connections, and you're just traveling around. And so the way that you would discover something like distance is by traveling through that world, which is effectively inventing some sort of successor function, which is effectively sort of rediscovering the definition of natural numbers from just one element, right, or something like that. And I find it very exciting because, I think we have just at least sketched the proof for the fact that we can have something that is very analogous to functions and vector fields and directional derivatives and so on. So we actually find the algebras, and it will be actually interesting to see. And I have some colleagues that will answer these questions immediately, because I am a bit rusty with my Lie theory. But the moment that we put together these axioms and it's like, okay, this is a Lie algebra, then that's going to be immediately known which Lie algebra it is, right? Like we're gonna. I'm a bit. Yeah, because this will be Lie algebras over the field of over F2, right? So
right.
So I mean, these things have been studied for sure. But anyway, I'm a bit concerned that these things are zero automatically, but I don't know. I hope not. So can I find it? Lie algebras over.
But this may have been, I don't know, the at least in its modern, certainly in its sort of revamped form, this may have been our first serious live institute breakthrough that's been live streamed or recorded.
Oh no, this is great. I'm so happy with this.
I'm very excited, and not least because so I'm kind of excited by the idea, because it's not really something that I'd thought about before, of like that higher arity Lie algebras might have modifications to the Leibniz rule, or where you would get boundary terms that, as we now suspect, effectively emerge as a consequence of the fact that certain terms don't go to zero in, say, F3, which would go to zero in F2. I never really thought about that before, but that's a particularly cool application area.
Okay, so I just found some papers that classify the algebras over fields of characteristic 2, which is F2 being a particular case.
Yeah.
So I think we're quite safe.
If it's not totally trivial. I mean, people wouldn't have written about it if they all went to zero, right?
Yeah. I would love to see something like, here's a Lie algebra over F2. I don't know if I'm gonna get it in this paper. Okay, classification of, oh, this is from last year. Interesting.
What I really like about this is that this is okay. So if this insight is kind of correct, it's part of this much more general class of kind of there's this statement that I've heard a few people make, for instance, that the like spin networks in loop quantum gravity. The right way to think about a spin network is that it's effectively a gauge theory where the gauge group is Z2, right, or Z2. So it's like the simplest non-trivial gauge group that you could imagine defining would be a Z2 gauge group, and the gauge theory that you get from that is effectively characterized by a graph whose edges are irreducible representations of some compact Lie group, and so you get effectively a spin group as you get a spin network as a sort of natural way of representing a Z2 gauge theory. In a sense, what this idea would be hinting at is that graph theory is somehow the differential geometry over F2, in some sense, which is, I think, which is an insight that sort of makes a lot of sense when you start to think about it, but it's not a way I've ever heard graph theory be characterized before.
No, that's same, and that's why I'm getting excited. Sorry, I'm just scouring quickly to see that some non-zero example of a F2 Lie algebra.
Yeah, please.
But wait. I might even, because it might be the case that, so we have the notion of derivation there. Now the notion of Lie bracket is just the commutator of those derivations. So maybe it's easier to see if there should be a reason why a commutator is always zero. Why a commutator of derivations is always zero in.
But hang on, but that should only be true in the. If this analogy is exact, so to speak, that should only be true in the symmetric case, right? In this. Hang on, I can't remember. Am I sharing? I'm not sharing.
No. Yeah.
That should only be true in this symmetric case, right? Because in general, in cases where you have a torsion connection, the Lie bracket of your vector fields will not vanish.
Well, if that's actually, if we could check that, I mean, this might be too long for one live stream, but
yeah, sure.
Yeah, because we are like past the 2-hour mark, and I think it's becoming less efficient. But but we should certainly make a compact, because if we can check. I mean, this. I mean, yeah, go ahead.
Because right now your definition of the derivation is only doing pointwise evaluation of the function at the vertices. It's not using any information about the weightings of the edges. In other words, it's not using any information about the connection. So it might be as simple as you just take that thing and then you divide it by, the edge weight or something sort of in between them. And if that's what you do, then I think
okay.
then I think it's kind of trivial that if you have that the Lie bracket of your vector fields will only vanish if you have a Lebesgue connection.
So no. So I was thinking, because the problem is the weights here. Okay, so actually, as advertised, at least for the audience, someone in the audience kept like my statement from like 30 minutes ago. Which I said, I think I know how to do covariant derivatives, but first let me do directional derivatives.
Right.
We actually figured out directional derivatives. This is amazing. I mean, it's...
no, of course, that's a really good point. So of course, the directional derivative doesn't care about the connection. If you make it care about the connection, it will be a covariant derivative. Yeah, okay, fine.
Exactly. Yeah.
This is easy.
Yeah. So I would say, I mean, I'm just bugged by this question because, I mean, I've been so hunted by... defining objects and then having them be trivial, it's like, or be non-existent. Like empty definitions is the bane of my existence.
Directed edge doesn't care about directed edge weight. By making it care about directed edge weight, which by dividing, we get a covariant derivative, would be the claim.
I would say so. I think covariant derivative will basically just mean, okay, so, yeah, isn't it true? Wait. Isn't nabla x, when you do a covariant derivative, isn't nabla x like, covariant derivative with respect to a vector field x?
Yeah, exactly.
Isn't that a vector field? No, that's an anchor map, right? That's an anchored.
Right.
What is, it's not a vector field, right?
No, you would evaluate it on a vector field.
No, I know. What I mean is that.
Yeah. But no.
It behaves like a derivation. It behaves like a derivation, but not like a vector field, right?
Exactly. Yeah.
Because it acts on vector fields when you put an F at the front. Wait, why is it not a vector field? Nabla x is a differential operator of degree 1, right?
Right.
It's not a vector field. It's not a derivation. Why is it not a derivation? It is a derivation of the functions. But...
My understanding was that it's a derivation, but not a vector field. But
that's the same thing. Derivations and vector fields are the same thing.
Okay.
Differential operator and vector fields are not the same thing. Nabla x.
This is you're exposing my terrible knowledge of analysis here.
Well, I mean, this is more like geometric, differential geometry, sort of differential operator theory. It's not so much analytical. It's like this. I mean, you have the. Why is it? I mean, nabla x. What object is nabla x? It's not a vector field, right? I think it's just a degree 1 differential operator. That's the problem, because it takes. When it takes a function, it behaves like x, right? But when you take the commutator, of course, what am I saying? It's not a vector field because it sends vectors to vectors. What am I saying?
Right.
Of course, yeah. Sorry. Yeah. What am I saying? Yeah. So it's okay. So it's but it's not a 1-1 tensor because it's not bilinear.
Oh, that looks terrible.
Exactly. Yeah. So what am I saying? Yeah.
Carlos thinks this is not a vector field.
It's not a vector field. That's certainly not a vector field. I mean, it cannot be. It's a 1-1. It gives a field of 1-1 tensors. Well, not really. It's a vector to vector map that is I stand by my statement. It's a degree 1 differential operator. It's, so it takes vector fields to vector fields in a differential operator way, meaning that if you have f times a vector field, then it does a generalized Leibniz rule. So it does derivation on f, which is just acting with x, times the vector field, plus f linearly nabla x on the vector field. So yeah, it is So, okay, so the question is, right. But okay, but nabla x on functions is still nabla x on functions is the same as x on functions, right? So the sort of degree 0, the component, the zeroth component of the differential operator is a vector field, is a derivation, but it is in general just a degree 1. Okay, all this I was saying because when you assume a particular distribution of tangent vectors, I guess that's where the analogy becomes a bit muddled here. I mean, it's not that it's anything wrong. It's just that it seems like a parallel transport is just a directed graph on the graph, on the underlying graph, and a vector field is also that, right? So actually that might be an interesting. A vector field is a unique assignment of arrows to vertices, right? So you won't be able to have like two arrows pointing out of the same vertex, right?
Right.
For a vector field. I imagine that might be the case for a parallel transport. So
yeah, I mean, so parallel transport is interesting, and this hints at the fact that this notion of connection is strictly, in some sense, strictly more general than the standard differential geometric notion of connection. Because, for instance, the very, very trivially, because we're dealing with finitary objects and the graph topology is not, is fairly unstructured. The cardinality of our tangent space can change as we move around. It will change as we move around. So there isn't just a straightforward way of saying, like, give me, take all the tangent vectors in my tangent space and parallel transport them and tell me what the tangent space is at some other point, because the tangent space at that other point might be strictly larger than the tangent space you started from.
Sure, yeah.
So your connection is doing something strictly more general than a standard differential geometric connection.
I mean, because if the analogy was that the connection was the metric was the undirected graph structure on the vertices, and then some directed graph structure on the, possibly weighted a bit, but for now just some directed graph structure on the vertices, then I mean, the vector field, as we've just shown, will be again some directed graph on the vertices, right? So it seems to me, and this would be a cool thing, right? So a connection we've seen is more than a vector field, because even if you just think of it as a what people would say that the vector field wait, what am I saying? That when something is tensorial or not, right? This condition of tensoriality, which is quite classic in physics, you change that you're changed under coordinate transformation accordingly, blah blah blah. All that might also have a finitary graphic analog here, right? So
sure.
So it might be that, and this will be super cool actually. I mean, again, I'm getting excited, but it might be that tensoriality is some simple condition, a graph theoretic condition, right?
Right.
Yeah, that's right.
What have I done? Okay, so here's,
Yep.
I think, an example of a
That
vector
looks
field.
like a vector field to me. Yep.
So let's note that down. So we've got, unique assignment of one outgoing directed edge to each vertex.
And
And
then you
that's
can
it.
see clearly, right, that with that definition, just if you want to make a note there, just for completeness,
Hmm.
that maybe a different section on top of vector fields and graphs is like functions and graphs, just to record it, like
Oh, right, yeah. Okay,
just
sorry.
to say that it's an assignment of
Unique assignment of
yeah.
one. Are we saying one element of F2?
And let's just say field value. I mean, we can,
Yeah, one element of a given field to each vertex.
yeah. And then it's obvious then that you can act with the definition of the finite difference derivation, right?
Right.
You can clearly act on a function to get a new function on the same graph, right?
And then I guess so. Natural thing is tensor fields would be assignments of tuples of outgoing directed edges. Right.
Yeah, and that's interesting. So okay, yeah, obviously we have the entire textbook of differential geometry definitions to,
Right.
to
Right.
like go over. But that's
of one-
actually interesting.
N tuple of outgoing directed edges.
Okay,
So-
here's an interesting question.
Uh-huh.
Again, I think this is it's better for like some kind of closing.
Yeah, sure.
Closing sort of like thoughts, and because I think we should
We'll talk.
meet sometime early next week. I mean, as soon as maybe next Monday or Tuesday, we can even, if you are happy with that, we can even say to our audience to be continued, and for things to continue very explicitly, because
Well, there has to be a follow up to this stream. I think.
oh no,
that's-
for sure, no. But
that's
what I mean is that as early as next week or something, right?
Sure.
Absolutely follow up. I mean, many, I imagine. But so next interesting question is, how about the metric? In what sense do we have? Because it might be okay. Let me gather my thoughts and make one cohesive sentence. So we know that the metric structure is analogous to this graphical undirected graphic structure. Fine. How about? So that's the distance construction, right? How about the angle construction, right?
Right.
So-
Yeah, exactly.
yeah.
In other words, it's very natural how you would get Ricci curvature or something. How would you get Weil curvature?
Yeah. So I would say I have a. I mean, there's kind of an obvious. I don't know if it's obvious, but on your tangent, given a tangent space, right? So given the natural tangent space induced by a metric structure, right? So that kind of situation. The question is as follows: if we specify two of those red edges,
Mhm.
can we assign an F2 value to them? I would say there's a natural answer to that, which is, are they commutative in the graph or not? That's a binary question with a binary answer, right? By commutative I mean, do they point to two vertices that are connected
I see.
via the metric?
I see. So hang on. I'll just do this visually, right? So you're saying that so these two would be commutative, but like this one and this one
They don't
I
seem
think
to be exactly.
not be commutative.
Exactly.
Right.
Yeah.
Okay.
That's
and
a
so-
question. That's a question that intakes two vectors
Yeah.
and outputs an F2 value.
I see. So your claim would be that the angle between this and this would be 0, and the angle between this and this would be 1.
The other way, I would say.
Wait. So if
I guess. Wait.
Let's be clear. Are we talking about angle or inner product? Like, or
Yeah. Right. Yeah.
Because I agree the projection of this onto this maybe should be 1, but I think the angle should be
Ah, okay.
Zero.
Yes. Sorry. Yes. Angle. Yes. Sorry. Yes. Yes.
Whereas the projection of this onto this should be
Yes.
zero.
Yes.
and the
Yes. Yes.
angle
Yes.
should
I was
be-
thinking of inner product. Yeah. Yeah. I was in.
Right,
Yeah.
right, right.
Yeah. Yeah.
Oh,
Sorry.
like maybe the angle should be pi or something. I don't know, but like
Yeah. Yeah. Yeah.
whatever.
Yeah. Yeah. No. But no. No. But that's the point. Like I was trying to think of a bilinear form, right? F2 bilinear. I mean, the fact that
Right.
that's F2 bilinear, I think, I'm gonna say it's trivial. I don't know. But,
Right, right. Okay, so let's make that our so angles angles in tangent spaces in graph tangent spaces. Yeah, let's make this our last comment, so to speak. So we take take the out component of this drop one directed edge, 1 comma.
oh, this is
That-
super exciting. This is
Yeah.
This is super cool.
Um,
And that's the.
all right, so that's our tangent space again. So now, but then we want this, and so we want to say if we take the endpoints of each of those, so those are our tangent vectors. We take the endpoints of those, and then we simply ask, I think. So we do find shortest path in the graph.
In the
So we
graph,
take
in the undirected graph, I would say.
Right. So we do tuples of that comma 2. We take all pairs of those. And then we say yeah, find shortest path in the overall undirected graph.
Yeah.
We just do find shortest path first of that, last of that. Oh wait, what am I doing? Oh, sorry, no. Sorry, I'm being an idiot.
So much potential here.
There is. Okay, and then so we just take for each of those couple there, and then we say okay. So if the length of that is greater than 1, so in other words, if there is a path, then we say that the angle is 0. Otherwise, we'll say the angle is 1. No, wait, no, that's
Isn't it easier? Wait, isn't it easier to just directly ask? There's no path finding. It's just ask. Given two edges.
Oh, it's just it's literally, is there a directed edge, right? Between them.
I mean, because we have the data of the underlying graph, right?
Right. Exactly. Yeah.
So you're just asking, are those is that pair an edge of the graph?
Yes. Right. Exactly. So we're just literally saying if member Q edge list graph, comma, directed edge, first of hash, last of hash.
Sure.
So this is actually giving so it's saying if they are connected, and we want to exclude the self pairs, so to speak. First of hash equals last of hash. Select no. Exclude those. Okay, so 4, 8, 5, 4. So yeah, okay, right. So this is our function that's saying so it's assigning an angle to 0 if they are connected by a directed edge and 1 if they're not. For all pairs of these particular vertices.
Yep.
So we'll say that.
So I would say that's the template for that should be the template for that's a tensor. That's a finite discrete. Sorry, it's a discrete analog of a tensor. If everything that we did today makes any sense, this should be an instantiation of a discrete 0-2 tensor, 2 covariant tensor, right?
Exactly. Okay, so that should be our starting point for next time, is to check whether that actually works.
Yep.
Whether that actually makes sense. So assign an angle of 0 if the endpoints are connected by directed edges, and
undirected. Right?
If
endpoints are connected by undirected edges.
Okay, sure. But in this case, they'll be connected by directed edges if and only if they are connected by.
Sure, because of the construction. But I think it's interesting. No, but I think it's important because the distinction is the angle structure is only dependent on the metric structure.
It doesn't care about the connection.
Exactly. Yeah.
Yeah. That's fair. That's fair. Okay, no, and that's an important conceptual distinction. Going forward, we should try and make that distinction. Yeah, I agree. And one otherwise.
Yep.
Great.
That's amazing. Okay. I mean, I didn't imagine I would feel so much sense of progress in one live stream. So I'm very happy.
Good dopamine rush. Yeah.
Absolutely. No, this is really cool.
Excellent. We are definitely making progress.
Yeah, and I mean, this is the thing that I told you. I mean, for the audience, for context, I mean, we had this conversation, and I had to qualify all my statements and to sort of like temper my excitement because I didn't know whether there would be an obvious Lie algebra lurking around. And modulo there being some statement that says F2 Lie algebras are all 0, which doesn't seem to be the case from a principle. You know, I would have probably found, by the way, if you try over F2, that's going to be 0. Then, you know, this is very exciting. And the thing is, if I find some examples around the internet that F2 Lie algebras make sense and are non-zero, then what is exciting about this is that as a very simple sort of spin-off from this is we can just generate a lot of F2 Lie algebras in this way, right? And this is for the Lie algebra audience, which is non-trivial, certainly. This might be an interesting source of finite Lie algebras, right? Like this is because I mean I was just quickly searching. I had never looked. I have to admit I had never looked into finite Lie algebras, like ever. By finite I mean on finite sets, right? Like not finite dimensional. And obviously finite only makes sense. Non-zero algebras are going to be over finite fields, right? I mean, if you have other fields that are not going to work out. But the point is, if you have a way to generate, like, if effectively any directed graph, right, gives you a Lie algebra, because it's you know, or even just a graph, any undirected graph, it gives you a Lie algebra of derivations of vector fields on that discrete manifold, whatever, right? Then, and those are finite Lie algebras, then suddenly you have all the machinery of graph theory to use in the aid for searches and classifications of these finite Lie algebras. Not that I care about that that much, but I am sure that we can go to some crowds and say, look, we found this pattern, we found this way of finding Lie algebras from purely graphical data. Go on and enjoy yourselves. You know. So, but it's completely spin-off. I mean, it's an offshoot of something that I'm not even that excited about, which is this entire program of discrete differential geometry and trying to recover all these notions of tensors and metric structures and all those things. But it was interesting that we had to make this. It was super interesting that we had to make this point of F2 has to be F2, and then it turns out that F2 questions are the ones that really make sense. I mean, I'm kind of surprised at myself that by restricting the angle question to be valued on F2, then it was completely natural to define it, right? And it doesn't seem to be another. I mean, can you see an obvious alternative to define an angle or something like that? I don't see a unique, right?
No. But I mean, the other thing that's exciting about this is that it's one of the few constructions I think we've discussed that as far as I can tell, maybe I'm missing something, generalizes very obviously to the higher arity case, right? So, you know, because the analog of the binary question of are these two things connected by a directed edge is an F3 question for a ternary hyperedge, right?
This is super cool because, I mean, this is connecting many different branches of interests of mine. I mean, just as a, but also I think it is legitimizing my confusion and the confusion of many, not just mine personal, but like the confusion of many in these questions of higher arity and higher order stuff. The fact that we had to go to this sort of like fringes to get analogs and so on. I don't know. To me, this is just super exciting because it's pointing towards something that is much broader than that. Just because I mean, a lot of the time when in mathematical physics, just for maybe a closing thought for the audience, when I was a PhD in Edinburgh, I mean, people were aware of this sort of like spin networks and, you know, loop quantum gravity and all these kind of theories, and a lot of people had this suspicion that why would I busy myself with the task of finding discrete versions of the things I know how to do continuously, if the continuous models are more effective and the discrete models are just still need to take some kind of limit to the continuous case, right? And I think that what excites me about this is that in a way I'm understanding the continuous models better by having this very finitary sort of concrete small examples of what things are, right? And if you were able to really make the case that a metric is an undirected graph and parallel transport is some directed graph structure on top, and vector fields are like distributions of edges and all those kinds of things, then suddenly the kind of even the teaching of differential geometry can become quite different, right? Because then
I was just thinking that, like, because I haven't taught a formal differential geometry course, but I've taught sort of, you know, introductory general relativity stuff.
Sure.
And it's like, if I could have shown a picture of this to illustrate what a tangent space is, that would have been so useful, right?
Exactly, right. Yeah. I mean, the thing is, my intuition was very much that, and in my lectures when I taught, because I did teach some like classical differential geometry, and when, you know, but so I like to do it in a intrinsic way, so when they encounter manifold theory they are comfortable with, oh, we have to do this in coordinates and then the general thing and so on. And I did have this sort of like on the blackboard very clearly, is like, think of tangent spaces as the possible directions and so on, and like, and effectively my pictures would kind of look like that, you know, like points and then scatters of finite scatters of arrows and so on. So I'm very glad that we are building a mathematically rigorous construction to actually show that these things are legitimately to be thought of as manifolds or tangent bundles, or and the thing is, there's no shortage for, again, to the point of the possible project that is gonna hopefully start next week or whenever we formalize the agreement with a future fellow. Then I mean, there's no shortage of, you know, homework list, you know, like you go to a differential geometry book, it's like, okay, here's whatever chapter 3 differential forms, okay, here we go, let's see what this means in this context, right? Or right. You know, it feels very exciting. Yeah. It feels very natural, and
absolutely we have enough here to keep several people busy, I think.
Yeah.
But yeah, no, it's an interesting point you make about, like, the, you know, Lie groups of the algebras have not really been considered very much over finite fields. That was kind of, I remember looking into this a little while ago, and bizarrely enough, like, one of the very few pieces of literature I could find about this was Turing wrote a paper like many decades ago about finite approximations to Lie groups, and that's like one of the very few things that's actually been written about this. But yes, I agree. It seems to be not a particularly well studied area, and it's entirely possible that the reason it's not particularly well studied is there just hasn't been any systematic way of generating examples of these, you know, non-trivial examples of these things. And this might be, you know, such a systematic method, right? So it's many exciting directions.
Oh, this is lovely. I'm enjoying this very much. I did not expect. I mean, I was looking forward to this because I wanted to, like, sort of share ideas and sort of like have some, but I did not expect as much sort of like conceptual progress in understanding and the picture. It's very nice.
Right.
Yeah.
Right.
Very cool.
Excellent.
Anyway, should we close it there? Or
let's close it there. And yeah, as you say, I think maybe let's try and schedule another stream, possibly for around the same time next week, if that works for you.
I think that works for me. Let me just double check my calendar, but I mean, maybe should we close the stream and then
sure, we can discuss this offline. But no, thanks everyone for joining.
So much, but it's likely that just for the people here, it's likely that around the same time next week we're gonna have the same thing. But do watch out for the announcement on our social media, and again, if you want to keep updated on Institute activity, we have an internal Discord where we post about our activity, and we are ramping up, so we expect it to be much more active in the coming weeks as we are getting back into rhythm. So I'm gonna share the link to our community page, both on Twitch and YouTube. We have a considerably smaller viewership on Twitch than YouTube, which I think is a good thing. But we'll share the link on both. So feel free to follow that link, and you'll see sort of a Discord icon there. You can just follow there, and then you join the community. So yeah.
And also, I mean, the other thing we mentioned this in I think on our last stream, or this maybe our launch introductory stream. But you know, we're still kind of trying out these different formats. We're still trying to work out exactly what our live stream structure is going to look like going forward. As I say, this was kind of the first that we've done of you know, at least in this form, of a serious kind of collaborative research stream, which I think worked very, very well as a format. And you know, we can't promise necessarily the same density of ideas and breakthroughs in future. But, you know, we'll try to maintain that. But so let you know, if you enjoyed this, like, let us know. If you didn't enjoy it, also let us know. You know, if you'd rather see, if you'd rather have kind of more you know, philosophical kind of discussion type streams, or you want to have you're less interested in seeing us try and work through a problem, but you actually want to see kind of more polished, you know, sort of finished presentations of work that's been done, let us know, right? We're still trying to get the balance right between, you know, between these different kinds of content that we want to be able to provide. But I at least had a really great time. It seems, Carlos, you also had a good time. So these are very fun to do. But yeah, so let us know whether they were enjoyable to watch.
Yeah, absolutely. It was great. So I'll see you all probably next week.